Okay, for the last speaker in this session, we are honored to have Professor Minhua Chen from CTU to talk about dollar second kg CO2.
Thanks for having me. Although I'm not a student of Stephen or postdoc, but I do work with Stephen, especially in the past several years, and learn a lot. And also Adam has been, we have read a lot of papers of Adam. Not all of them, but I think the substantial percentage of them. And so I guess since from several talks, we have a culture from, it's more like a culture competition. We have somebody like Chi Wei from, Singapore culture. And then I think the previous speaker from UK are very enjoyable. So I think almost I should do something in the Hong Kong share to increase some cultural diversity of this workshop, okay? So now, because in the US, we now, we are sitting in a quiet room just by talking. But in the Hong Kong, things can be very different. Okay? I don't know whether or not you can hear it, but this will be, so Stephen, if you're in Hong Kong, this might be the way that you're going to celebrate your birthday, okay? Okay, right. It's actually saying in Cantonese, it's just a happy birthday, wish you have this day every year, wish you have this night every year, right? So I guess it's the local culture difference, okay? Okay, all right. So now let's move on to the talk stuff. Okay. Do I see anything? Where's my mouse? Okay, here we go. All right, so dollar second and kg CO2, I guess you can be wondering what this talk is about. Well, here we go. It's all about how do we solve the optimal power flow problem for people from power system. This is the problem. It's equivalent to the network utility maximization problem you solve in computer networks. And we want to solve this in real time so that we can get a sustainable development of the society and our planet, so to fight climate change. And this is not just done by me, but the whole deep OPF team, that some of them are in Hong Kong, and also with Stephen participate, and we learn a lot from Stephen. Thank you, Stephen. So first of all, climate change, big deal. If you care about fighting climate change, probably you care about power system, because power system contribute more than 25% of the global greenhouse gas emission. And major countries around the world, including China and the US, although they are fighting now, but they are aligned in this target of trying to decarbonize their power grid. I think Stephen might talk about more in his talk tomorrow. And you can see that all target to have a substantial percentage of their power generation coming from renewable. Right? So some other country, even more ambitious, like Denmark, they target for 100% renewable by 2030. Renewable is great, except one thing, they're volatile. Okay? 80% of renewable are wind and solar, and these are their generation over the time, so you can have a sense. Okay? And when you have a volatile renewable, you create some problem to the power grid, because power grid is, I would imagine it's like something, it's a very special supply chain that requires supply and demand to balance in every single minute, every single second, every single millisecond, okay? So when you try to do so, actually at the minute scale, you are required to solve this optimal power flow problem, okay? In the past, utility may just need to solve this problem half a day, but now the US market required to solve some version of this optimal power flow problem every 5 minutes. In the future, potentially people are talking about every 1 minute. Okay? And when you're talking about OPF, essentially it's trying to minimize the cost. This is where the dollar comes from. The cost of generation so that you can serve the load over power network. So that is the problem. That's what the problem is. The problem, mathematically, it is a non-convex problem, a very challenging to solve. I know Chi Wei loves a non-convex problem. So this is a problem that I think Chi Wei has been working on for some time. And the grid operation nowadays, because of the renewable, they require to solving this problem very often. But the challenge is that the state-of-the-art solver is not fast enough. Okay? Basically, the current practice, no matter what they will do it one way or the other, either you solve some approximate version of the problem, or you let the iterative solver run until a certain time window and you stop there, and you take whatever solution from there and you rely on the reserve to help you to balance the mismatch. Okay? Because of that, many case studies shows that even have, say, improve the current solution by 5%, you can go to see tens of billions of dollars saving globally. So it's something has a big room for improvement. Okay? And Stephen and his group have worked, come up with something very nice in the past of how we can solve this like by doing convexification, right? So under certain condition, solving the convexified problem gives you the exact solution to the non-convex problem. This is super cool. Very nice result. The only concern is that the condition under which this holds may not be satisfied in practice, right? So so we are still stuck with the current practice for many of the situations. So starting from 2018 or 2019, then Stephen and I met on an E-Energy conference, and then we said, maybe there's something can be do differently, and here's our view. So thinking about how to solve a constraint optimization problem, there is, I give you an input, you give him an output from the solver, right? So implicitly, the solver characterizes a load-to-solution mapping. So if you think about power system, and this, by the way, this is for DC OPF, just for illustration purpose, you can you vary the input and plot the output here. You can clearly see there's a nice mapping between the input and output. So this hint on possible way to solve the problem quickly when in the runtime. That is, maybe you can learn this mapping offline, like you can solve this problem many times and collect a bunch of samples, and then you train your neural network, train something to learn this mapping. Once you learn this mapping, you give me an input, I give you output immediately. So hopefully this reduces the complexity. And indeed, it does, as you will show later. Okay? Then the only question, the number one question is, okay, is this a heuristic or something you can justify? Okay. Without further going into the details, the quick answer is yes. So mathematically, you can prove that for the OPF load-to-solution mapping, it's guaranteed to be continuous almost everywhere within the load region you care about. Okay, that's nice thing, continuous. And then for continuous mapping, for neural network 101, we know neural network is a little bit like Taylor series. So give me enough terms, I can approximate any continuous function. For neural network, you give me enough neurons, I can approximate, I can learn any continuous mapping arbitrarily well. So this lay down sort of the foundation, like the justification of why neural network could be an approach to learn the mapping and solve the problem. Okay? And this kick off some investigation. For instance, this is something that from our joint exploration. That is, if you apply, you can use this idea to solve an ACOPA problem over 2,000 bus network, which is considered pretty substantial. And you can speed up, attempt a speed up of 4 orders of magnitude, right? So just based on this neural network idea, okay? And further, we also apply this to Australian network with realistic low profile. It seems to work okay there as well. So I think this is some justification why this may work, okay? And of course, this seems to be something that is different from what people were doing when they try to solve OPF problem. Indeed, many of the constraint optimization problem. So this deviation not only gives you some new way to think, but it's also a new challenge to address. For example, I think many people care about neural network where they care about how can can you guarantee neural network solution we're going to satisfy these hard constraints, like equality constraint, inequality constraint, etc. Okay, so there is a line of work there. So I will not dive into the detail of that, but if you have interest, I'd love to talk about that. But rather, I would like to talk about something that is more recent, so I think I want to hear feedback from you guys so that we can see what we can move from the frontier. Okay. So by the way, this is all the society's effort up to this last month, and you can see there's more than one group, actually more than one society, including from Power Systems Society as well as Machine Learning Society. They all have a different contribution to the overall theme of machine learning for constraint optimization. Okay. But if you step back, I would say the most of neural network that you design for OPF problem, they are sort of problem oblivious. Right? They are ResNet, they are ReLU network, RNN, transformer, graph neural network applied for OPF. But I think from today's keynote, that Shrikant saying if there's a structure, you should utilize the structure. Okay? So maybe we want to think about, can you do some design that exploit the problem structure? And if you do so, what would be the benefit? Okay. I would like to show one example today. I would like to show that using this two-stage AC OPF as an example. So this two-stage AC OPF appear when you do market cleaning or you do any decision making with a lot of uncertainty, especially from renewable. Basically, these two airports in this decision making, you need to make the decision in a sequential manner. When you made the first decision at first airport, the second decision time, there's some uncertainty. It hasn't been reviewed yet. For instance, renewable generation, etc. But when you made the decision, you want to purposely take those potential uncertainty into account so that the overall cost is minimized or the overall system safety has some guarantee. Okay? So there is a high-level idea of why you want to care about two-stage ACOPF problem. So typically it looks like this. You have a first stage, you want to make a decision, mu0, and in the second stage, instead of, for most of the, like the distribution uncertainty, you will not be able to write out their expectation of the course. So you're going to do sampling, like do a bunch of scenario sampling, K scenarios. For each scenario, you try to come up with the corresponding optimal decision for that. So they minimize the total cost from the first stage and second stage, subject to all the constraints you need to satisfy in the first stage and second stage. And then all the second stage, the first stage's decision will affect the feasibility region in the second stage, right? So this is, you probably also see this problem of this structure in this inventory management and other application domain as well. But nevertheless, for ACOPF, two-stage ACOPF, very difficult to solve, huge problem size, this problem non-convex. So it's unclear how you can solve this problem fast. Okay, and as an example, if you just look at about 100 bars and 100 scenarios, this can take 30 minutes to solve on the reasonable fast this CPU. And if you're going to take a problem oblivious and design, you say, okay, give me the order input, like this is the demand from the first time airport, and D1 to DK is the K scenarios input for the second stage. You give me a neural network, I learn the solution, input the solution mapping. Hopefully that can do it well. But this will run into the situation that you have a dimension explosion. Because as you have more and more these scenarios, the more and more larger and larger the input size to the neural network is, then you may need more neurons in the system and a lot of training samples to train. Okay, so we don't want to do that. So there's one. Okay, great. There's one observation that a student make, which is very nice. He says that, you know what, for a problem like this, if you change or permute the input to the second stage, like the D1 to DK, you permute the variation. Like the optimal solution on the mu0 doesn't change, right? Because there's symmetry there. So if you change the DK, it only affects the UK, and the UK is here, and the UK's contribution to the objective value is the same, etc. Okay? So there is some permutation invariance there. So indeed, what you mathematically can prove for this kind of two-stage problem, the optimal solution to the first stage can be written simply as a function of only two variables, two, regardless how many scenarios have. And so then it only involves some of the simple, up to two-stage, two variables mapping. So we can prove this mathematically. So this is the problem structure we'd like to explore. So once you have this structure, this idea perhaps it could be simple. So you just need to train neural network to learn each of them and combine them in a way so that it respects this mathematical structure. And that's what we did. So for the stage one network, mathematically, inspired by the mathematical the structure, you can design neural network to have the different second stage input pass through this neural network sequentially, and then sum up and combine them with the first order things to give you the first stage input to give you the first stage optimal solution. And once you have an optimal solution first stage, you get to the second stage and to give the individual solution. So in this way, good news, no dimension explosion. Okay, exploring the problem structure does help in this case. And you can explore prove the approximation error, etc. So we'll not dive into that. So we can chat offline if you are interested. And second, perhaps this is not even more surprising in some sense. That is, if you have a mapping that is permutationally invariant, what does it mean is that when you prepare the sample data, some of the data may look entirely very different, but they look the same to the mapping, okay, to the neural that we want to train. In other words, they are redundant. So when you prepare the training data, you shouldn't just do uniform sampling across the entire the input space, but rather you would force an order there because you know anything other than this order, they are they're the same. You know, they are identical to any input in here, so you can remove them. So once you do so, you can prove that you can improve the training sample efficiency by a factor of k factorial, not just k, not just 2k, but k to the factorial, where k is large is close to exponential reduction, okay, of the things. All right, so there's some result just saying, these things indeed work, and you give you 5 order of magnitude faster than the existing solver. So that's what we want to say. So high levelly, what we try to, the takeaway messages here is that if you are considering try to solve a constraint optimization problem like the OPF problem really fast in real time, then perhaps you can think about using machine learning to trying to learn the mapping be offline, and when you're using online, then you can get a solution much faster. Okay. And second, that is to exploit some problem structure does help, is in particular for this two-stage optimization problem, but I believe that its application is beyond this two-stage ACOPF. So there's some future direction that is this is all great, but except when you prepare the training data, you still rely on conventional solver to solve it, give you an input to solution pair, but that itself take a really long time. So is there a way to address this issue? Maybe self-supervised learning could be a way, so we don't know. These things are still ongoing. So, so this is still, I think more and more research could be done along this way. So that's it. Thank you very much. So Stephen, this is the photo from last CDC. Yeah, thank you for the dinner. Thank you.
Any questions?
So you mentioned standard neural network architectures such as convolution, ReLUs, and stuff like that. I mean, ResNets and so on. I was curious, most of those ideas came from computer vision, learning images or something like that. I was just curious, why do they even work for solving something like OPF? I mean, is there some intuition as to why? I mean, later you talked about using problem structure, but I was just wondering, the first stage, you guys just simply used existing architectures that come from neural networks that are trained to recognize people or stuff like that. And I was just curious why it works for optimization problems.
You mean wider? I think for a lot of the problem structure, like the neural network structure, like the ResNet, they're also proven to be universal approximator, so that you can always exploit that part. And I think also people prove that, for instance, we prove that ResNet, if you use ResNet to approximate any continuous function, you actually can use a number of parameters you use is order of D, 1D reduction as compared to ResNet. So I think people are using that. Some other people are using graph neural network, maybe because ACO problem is more like the problem over a graph. So they think that there's inherent graph structure there, which I agree. And then I think there's people start to see some good performance there as well.
Yeah. So you don't use convolution layers and stuff? Or
convolutional
layers?
Convolutional layer. I think people, when they're doing this real-time OPF, they start to use convolutional layer. But I think maybe there's not a majority of them are not using like that. Yeah, RNN in solving standard ACOPF.
Thanks.
Thank you.
Yeah, so I guess regarding the training, you were saying you need to, of course, to generate examples, you need to solve OPF somehow.
Right.
And so is there any idea of how you generate those examples? Because is it just random Monte Carlo or something? Because it seems like the possibility that this would generalize, again, I'm not a big believer, I mean, I don't take it on faith. The fact that it will generalize to well would depend on what training examples you chose. So how do you choose them?
Okay, I guess the question is about whether or not these things as a performance guarantee in some sense. How does that relate to training? Okay.
Except that you don't have that, but
No, we have that. It's not that we don't have that. Well, the things that we
nobody has
right.
those neural nets.
Right, but of course, under some, of course, you always have mild condition on. When we generate training, what we have is your default load curve, and then we generate generate the load plus minus like X percentage, like 20%, plus minus 20%. Some people try plus minus 50% extra. You sample all this data, and then you fit into a neural network the OPF solver, like the Newton's method. You try different initial condition. So because you're doing it offline, you can afford to have more time to throw in different initial condition and pick the one that's give you good, firstly, converge, and second is good optimality. Yeah. So once you prepare that, you can start to train your neural network. Right.
Okay, thank you. Let's thank the speaker again.
Okay, thank you.